In this video, we want to talk about curve sketching and dealing with asymptotes and rational functions. So there is a lengthy process for a strategy for sketching graphs, and I'm going to do an example and walk you through all these. So I'm going to go through just what the steps are really quickly, and then we'll jump right into the example. So first, you want to find intercepts, if there's any x and y intercepts. When you have a rational function, you want to look for asymptotes. Are there any vertical or horizontal asymptotes here? Next, we want to talk about the derivatives and the domain. So you're going to find the first derivative and second derivative, right? We use first derivative for increasing and decreasing, and we use second derivative for concavity. The next thing we're going to do is we're going to find the domain of f, just so we have an understanding of that. We're going to do the critical values, and then we're going to use those critical values to help us find intervals for increasing and decreasing and relative extrema. Then we're going to look for inflection points, right? We use the second derivative for that. And then we're going to look at concavity, where the curve is opening up or opening down. And then finally, we're going to use all that information. I know it's a lot, so don't forget to take a big, deep breath as you do this to sketch the graph. So a lot goes into this. All right, so here's the example I want to do. So I want to sketch the graph of this. So this rational function, f of x is equal to 8 divided by x squared minus 4. It might even help to just see this, right? So this factors as 8 over the difference of two squares, right? So this is going to factor as x plus 2, x minus 2, right? So just so we have that. All right, so let's go through. I'm literally going to go through A through H here with you. Okay, so the first thing is the intercepts. So f of x is equal to, so again, it was 8 divided by x squared minus 4. Okay, so first off, let's do x-intercepts, right? So x-intercepts occur when y is equal to 0. But if you look here, right, if you cross multiply here, you get 1 times 8 is 8. 0 times, well, that just knocks it out. Okay, so that's a false statement. So there are no x-intercepts here. Okay, all right, so that's good. So what that means is, so just keep this in the back of your mind, right? When we go to sketch this graph, it's never going to cross the x-axis because there's no x-intercepts. All right, so the y-intercepts, or y-intercept, excuse me, this occurs when x is equal to 0, so you're just going to plug 0 into the function. So you get 8 over negative 4, right? So that's going to reduce to negative 2. So you're going to have the y-intercept is going to occur at the point 0, negative 2. All right, so if it helps, right? So just so it's clear, like, maybe as you get a piece of information, I'm just going to skip ahead a little. Boom, right on the graph. I'm going to plot the y-intercept, okay? So we got the intercepts. So the next thing says, all right, let's look for asymptotes. All right, so there's two types of asymptotes, right? So let's go back. F of x is equal to 8 over x squared minus 4. All right, there's vertical asymptotes. Okay, so in this case, you're going to look, when does the denominator equal 0? Okay, well, you get x squared is equal to 4, or x is equal to plus or minus 2 when you square root it. So you have two vertical asymptotes. You have one at x is equal to negative 2, and one is x is equal to 2. All right, the horizontal asymptote. Well, look here, the degree of the denominator here is 2, and the degree of the numerator is 0 here, right? So the degree of the denominator is larger. Okay, so we have a horizontal asymptote at y is equal to 0. Okay, so what I'm going to do is I'm going to take and I'm going to plot these on my graph just so I know. Okay, so I'm going to skip ahead in the slides a little here, writing it down. Okay, so I have a horizontal asymptote at y is equal to 0, so at the x-axis. So I'm just going to put a red line there so that helps me know. I have vertical asymptote at x is equal to -2. And I have another one here at x is equal to 2. And so you can kind of start to see like how this graph is going to lay out, right? Like it's going to have to butt up against these. Okay, so you're going to have to like figure out how to do that. And I'll show you. I'll show you. Don't worry. Okay. So the next one is derivatives and domain. Okay, so let's find the derivatives in the domain. So I actually have that for you done. So I have the derivatives here. I just did this for you just to save a little bit of time here. So you're going to have to go through and verify these for yourself here. Okay. And then so what is the domain? You know, you can just see the domain is obviously, it goes from -infinity to -2, and then it's going to go from -2 to 2, and then it's going to go from 2 to infinity, right? Because the only values you can't plug in are -2 and 2. So it's every other value except those, okay? So, you know, you could do it another way, right? Like the domain is equal to x such that x is not equal to -2 or 2 is another way you could do it. Or x exists in the real numbers except not equal to -2 and 2. All right. So the next thing it says is find the critical value. So you're going to look at your first derivative here, right? So f prime of x is equal to -16x all over, and then look here, x squared minus 4 squared. Okay, so the critical values occur when the first derivative equals 0. Well, so whenever you want to find when a rational function equals 0, you just got to look at the numerator, right? So when does -16x is equal to 0? That happens when x is equal to 0. And it also occurs when f prime of x does not exist. Okay, and so that's when you get to divide by 0, right? So that's going to happen at -2 and 2. So this function has 3 critical values. Okay, I'm going to put them in order. It's going to go -2 to 0 and 2, just there. All right, and what's really interesting here is you can see, just looking at our graph here, that some of the critical values are going to be asymptotes. So we know that relative extrema occurs at asymptotes, so there is going to be no relative extrema at -2 and 2, but maybe here there's going to be one. Okay, so we got these. So going back, all right, we got derivatives, we've got critical values. Now we got to do increasing and decreasing. Okay. So just to find this, okay, just recall that the critical values were x is equal to -2, 0, and 2. So you're going to use these critical values to carve up the number line. So you're going to have this interval, or your intervals. So your first interval is going to go from -infinity to -2. Then you're going to go from -2 to 0. All right, then you're going to go from 0 to 2. Okay. And then look, you're going to finally go from 2 to infinity. Next thing you're going to do is you're going to pick a test value. And you're going to pick something super easy, like -3, -1, 1, and 3. And remember, what you're interested in then is just the sign of f prime of x here. Sign of the first derivative. So our first derivative, f prime of x here, remember, going back, it was -16x all over x squared minus 4 squared. So all you're interested in, actually, believe it or not, is the sign of the numerator, right? Because whatever value of x you plug into the denominator here, it's going to be positive because you're going to square it, and you square the outside here. So f prime of negative 3. So what's negative 16 times negative 3? Well, that's greater than 0. Same thing with negative 1. It's greater than 0. When you plug in 1, right, you get 16 times 1. Negative 16 times 1, which is less than 0. And then f prime of 3 is less than 0 here. So here's what you're seeing. You're increasing from negative infinity to negative 2, and then also from negative 2 to 0, okay? And then you're decreasing, okay, from 0 to 2, union, and then from 2 to infinity. The only place you can have, and maybe I'll even put it here so you know that it's increasing, increasing, decreasing, decreasing. So look, you're going from increasing then to decreasing. Okay, so what that's telling us here is that you have a relative max here because you're increasing, increasing, and then decreasing. So we have a relative max at this point here. Okay, where x is equal to 0. Well, you know, that's great. What point was that? That was 0 comma negative 2, because that's the y-intercept. So going back, look, right here. We know that this is a relative max. Okay, so this point here is a relative max. All right, there's no other, there's no relative mins or anything here. Okay, so what's next? We got to find inflection points. Okay, so looking back, you have to look at the second derivative here. And so the thing with the second derivative, it's 16, and then in parentheses, I'll rewrite it. 3x squared plus 4. And it looked like it was all over x squared plus, or minus 4, excuse me, cubed. Okay. So inflection points occur where the second derivative is equal to 0. Well, you actually can't ever set the numerator equal to 0 and solve. It won't happen. Okay, great. So it's just going to happen where now you look where the second derivative doesn't exist. And this, again, is at the points where you're going to divide by 0. But the thing is those are vertical asymptotes. So what this means is there's no inflection points. Okay, that's okay, not a big deal. You still want to look though for concavity, okay? And concavity you look at where the second derivative either equals 0 or does not exist. So here that happens again when x is negative 2 and 2, okay? So what you're going to have to do then is you're going to have to set up your intervals. So you're going to go from negative infinity to negative 2. You're going to go from negative 2 to 2. And then you're going to go from 2 to infinity. Again, you're going to pick test values. All right, so I'm going to pick negative 3. I'll pick 0. And then I'll pick 3. And up here I'm going to put the second derivative again, okay? Because what you're interested in is you're interested in the sign of this second derivative. So you're looking at the sign of f double prime here. And here's how you got to handle this, right? Whatever value of x you plug into the numerator, it's always positive. So you only care about the sign of the denominator. So look, x squared, so negative 3 squared is 9. 9 minus 4 is 5. 5 cubed is 125. So this is greater than 0. F double prime of 0, though, if you plug 0 in for x squared here, you get 0 minus 4. Minus 4 cubed is a negative number. And then we see, by the same rationale as minus 3, the sign of the second derivative evaluated at 3 is greater than 0. So that means it's concave upward here and here. And it's concave downward here. So it's concave upward from minus infinity to minus 2. And then from 2 to infinity. And it's concave downward from minus 2 to 2. All right, so a lot going on here, okay? So what it does help here to sketch the graph is maybe get some extra test points here. And so look, what we saw was that it was increasing. Okay, so the only way it can be increasing from negative infinity to negative 2 and still butt up against these asymptotes is it needs to whoosh, come up like this. Well, look, then we saw it was increasing from negative 2 to 0. So it has to go like this and butt up against this asymptote. Then it was decreasing from 0 to 2, so down like this. And then again, it was decreasing from 2 to infinity. Well, remember, decreasing means you're going down as you go left to right. And it butts up against the asymptotes, like so. And that's what the graph should look like. On the next slide here, I have a little bit cleaner version so you can see it. But again, all it is just taking all the information you had to depict the graph here, okay? You know, also, honestly, when you go to do your homework, you can use the graphing calculator to verify this too, so that'll help you as well. All right, as always, as you begin your homework, I know this example, there was a lot in it, but as you begin your homework, if you have any questions, let me know.